Here's the thing. Manual transmissions are great, but if you aren't a masochist or enjoy having your left leg cramp up in traffic, or just generally someone who thinks stalling at a red light builds character, then a manual just isn't for you. These days, most people want to put it in D and go. They want the car to figure out which gear to use while they argue with their GPS about the fastest route to target. And so, to bring peace to the land, engineers came together and invented the automatic transmission, a device so complex that it makes rocket science look like a juice box. Okay, maybe we're over-exaggerating a bit, but for context, we're talking about hundreds of moving parts, all swimming in special oil, all controlled by a computer that's smarter than your cousin Jeff, who knows about cars. But how does it work? Well, get ready to find out as we're cracking open the most complicated, fluid-filled nightmare box ever bolted to an engine, the automatic transmission. Let's break this beast down. Okay, starting at the top, you can't have an automatic without a torque converter. It's basically the thing that connects your engine to your transmission without a clutch pedal. Because, if we're being honest, clutch pedals are for heroes and people who hate themselves. But what exactly makes a torque converter? Well, first up, we have the impeller, which is bolted to the engine's flywheel. This little bit of engineering spins whenever the engine runs. It's got curved blades like a fan, and it hurls transmission fluid outward using centrifugal force. Working with the impeller, the turbine sits across from the impeller, connected to the transmission input shaft. Basically, when fluid slams into its blades, it spins. That's it. That's the magic. Fluid goes whoosh. Turbine goes spin. Sitting between the impeller and the turbine lies the unsung hero of the whole system, a little something called the stator. This thing's entire job is to redirect fluid flow back to the impeller at the perfect angle, essentially multiplying the torque. It's like a hydraulic boomerang made of metal and broken dreams. But here's the wild part. There's no physical connection between the engine and the transmission. It's all fluid. You're just transferring power through oil. That's like trying to push a car by throwing water bottles at it, except it works because physics. See, when you're at a stoplight with your foot on the brake, the impeller is spinning, but the turbine is not. The fluid just churns around doing nothing useful. That's called stall. Not the bad kind where your engine dies and everyone honks at you. The good kind where you can idle without moving. When you release the brake, though, the turbine starts spinning, slowly at first, then faster. Mostly because the torque converter multiplies torque by about 2 to 1 at low speeds. It's basically free power from fluid dynamics. Honestly, that's the easiest way to explain what happens, but if that doesn't make sense, it's completely okay to call it magic. Because, honestly, all that just sounds like fancy witchcraft. Now, here's the problem with torque converters. They're inefficient. Fluid slips. Some energy gets turned into heat instead of motion, and the heat goes nowhere useful. Just a lot of college degrees. So, to fix things, modern torque converters have a lockup clutch inside. Basically, once you're cruising at highway speeds, this clutch mechanically locks the impeller to the turbine. This means no more fluid slipping thanks to the direct connection like the one in a manual transmission. But only this time, you didn't have to do anything except exist. The lockup clutch is controlled by the transmission computer, whose function is to mechanically couple the engine to the transmission at cruising speeds to improve fuel efficiency and prevent slippage. Now that you understand, or at least pretend to understand, all that, we need to look inside the actual transmission, past the torque converter and into the zone where gears do impossible things. See, unlike a manual transmission with gears sliding back and forth, an automatic uses planetary gear sets. Cool anime name aside, they're called that because they look like tiny solar systems. You got a sun gear in the middle, planet gears orbiting around it, and a ring gear on the outside holding everything together. And here's where it gets weird. You can hold any of these 3 components stationary and let the other 2 spin. That's because each combination gives you a different gear ratio. It's like having 6 gears in the space of 1. Compact, efficient, absolutely terrifying to rebuild. Let's break it down for those at the back. Say you hold the ring gear stationary. Drive the sun gear and have the planets walk around the inside ring while it's spinning. The carrier that holds the planets becomes your output. And just like that, you get a gear reduction, torque multiplication, and essentially first gear energy. Now, if you release the ring gear and hold the sun gear instead, you get a totally different ratio. Maybe second gear, maybe third. Depends on how the engineers felt that day. Probably tired, definitely underpaid. To make it crazier, you can even lock two components together. For example, if you lock sun to the carrier, suddenly the whole thing spins as one unit. That's your one-to-one direct drive, which is usually fourth gear in older transmissions. Today, modern automatics stack multiple planetary gear sets together. 2, 3, sometimes 4 of these things all work together like a mechanical orchestra, conducted by hydraulic pressure and a lot of prayers. But here's the question. Just how do you hold parts of the planetary gear set stationary? In fact, how do you choose which combination to use? Well, Jason, clutch packs and bands. That's how. See, clutch packs are stacks of friction discs. Some are connected to the transmission case. Some are connected to the rotating parts. They're arranged this way so when you squeeze them together with hydraulic pressure, they lock that component. Think of it like the clutch in a manual, except there are 10 of them and they're all wet and none of them have pedals. Got it? Of course you do. You're a genius. Now pay attention. This will be on a test. Each clutch pack is controlled by a piston. The piston is controlled by hydraulic pressure. The pressure is controlled by a valve body. And the valve body is controlled by either a computer or black magic. Jury's still out on that one. Now, let's look at bands. These basically wrap around the outside of drum-shaped components. They're there so when hydraulic pressure activates a servo, the band clamps down and stops that drum from rotating. It's elegant, it's simple. It's also why rebuilding these things costs more than my first car. So, how do they work together? Well, for a typical upshift from first to second, it goes something like this. Say you're in first. Clutch pack A is engaged, holding the ring gear. The planetary gear set's doing its thing. Low gear, lots of torque. The computer decides it's time to shift. And just like that, the valve body redirects hydraulic pressure. Clutch pack A releases, clutch pack B engages, and now you're holding the sun gear instead. Different ratio, second gear, and impressively, you felt nothing because it happened in 200 milliseconds while you were checking your phone. Repeat this for every gear, third, fourth, fifth, sixth, and you quickly see just how insane the whole thing truly is. Some luxury cars even have 9 gears now. 9! That's not a transmission, that's a full-on robot. Now, if you were paying attention, and I assume you were, your new question should be, what the heck is a valve body? The valve body is a chunk of aluminum with dozens of passages drilled through it. Hydraulic fluid flows through these passages, so valves open and close to direct fluid to the right clutch packs at the right time. In older automatics, this was purely mechanical. So you had things like springs, check balls, and centrifugal weights spinning based on vehicle speed. It worked kind of like how a sundial works. Technically accurate, but also deeply frustrating. Modern transmissions today use solenoids. These are electromechanical valves controlled by the transmission computer. The computer monitors engine speed, vehicle speed, throttle position, load, temperature, and probably your credit score. Then it decides which gear to use and fires the appropriate solenoids. The result? Smooth shifts that are perfectly timed and better fuel economy than any human could achieve by manually shifting. It's impressive. It's also why you can't fix your transmission in your driveway anymore. You need a computer and a degree in electrical engineering and maybe some therapy. Okay, it's finally time to walk through a full acceleration from a stoplight, because I know you're sitting there thinking, but how does this work in real life? Starting at the red light with your engine running. The torque converter impeller is spinning. The turbine is barely moving. First gear is already engaged because clutch pack A is holding the ring gear of the front planetary gear set. With your foot on the brake, nothing happens. fluid just churns. Once the light turns green and you release the brake and press the accelerator, the engine revs increase. The impeller throws more fluid at the turbine. The turbine spins faster. Torque multiplication happens, and the first gear ratio pushes you forward. Power flows through the locked ring gear. The sun gear spins the planets spin the carrier, and the carrier spins the output shaft, drive shaft, differential, wheels, you're off. As you go on and start to near around 3,000 RPM, the computer says, that's enough, time for second gear. And just like that, the valve body receives an electronic signal. The solenoid opens, hydraulic pressure builds behind clutch pack B's piston. The piston squeezes clutch pack B. At the same time, pressure releases from clutch pack A. This is called a shift overlap. For a brief moment, both clutches are partially engaged. Too much overlap and you get a tie-up where the transmission binds. Too little overlap and you get a flare where the engine revs spike. The timing has to be perfect. We're talking 50 milliseconds. That's faster than you can blink. Faster than I can process the sound of a dying engine. But if it all goes well, now you're in second gear. Different planetary configuration. Lower gear ratio. Less torque multiplication, but higher output speed. And you keep accelerating. As you go on, you repeat the same process. Different clutch packs, maybe a band engages, maybe another planetary gear set gets involved. It's a choreographed dance of hydraulic pressure and spinning metal and friction material getting very hot. By the time you're in sixth gear, cruising at highway speed, the lockup clutch has engaged in the torque converter. You've got a direct mechanical connection, and the transmission is in overdrive with the engine spinning at maybe 1800 RPM. That is until you need to pass someone and floor it. Then the computer downshifts, releases clutch pack F, engages clutch pack C, unlocks the torque converter, engine revs scream up, power floods through a lower gear. You blast past that Prius doing 55 in the left lane, and you did nothing except press your foot down. The transmission handled everything. That's the magic. That's also why these things cost $4,000 to rebuild when they inevitably explode. Look, I love manual transmissions. You know I do. But let's be real. Modern automatics are engineering marvels. And they're winning 8 speeds, 9 speeds, 10 speeds in some Ford and GM applications, shifts faster than any human, more efficient than any human, doesn't get tired in traffic, doesn't grind gears because you missed the synchro. Plus, they're putting these things in supercars now, Ferraris, Porsches, Lamborghinis, because even professional race car drivers admit that a good automatic shifts faster than they can, and that's with paddle shifters. Without them, forget it. You're rowing through gears like you're a rowboat while the computer's already shifted 3 times and calculated your fuel economy. The downside, however, is the insane complexity. I mean, when these things break, they don't half break. They fully break, expensive break, catastrophic break. The kind of break where the mechanic inhales through his teeth and says, "Oh." And you know you're about to take out a second mortgage. But when they do work, perfection, hydraulic, mechanical, and electronic perfection. But yeah, that's how an automatic transmission works. Torque converters, planetary gear sets, clutch packs, bands, valve bodies, solenoids, all working together to shift gears while you eat fries and sing along to whatever sad song came on the radio. If you learned something, hit that like button. If you're still confused, that's normal. I've been studying these things for years, and I still have nightmares about valve bodies. But if you don't want to be confused and have nightmares, subscribe for more overly complicated explanations of car stuff that could have been explained in 30 seconds, but instead took 20 minutes because I have issues. Leave a comment telling me how I got something wrong. I probably did. I left it wrong on purpose to make you feel smart. You're welcome. And remember, just because it shifts by itself doesn't mean it doesn't deserve respect. That automatic transmission is working hard. Give it fresh fluid every 50,000 miles, or don't, and deal with the consequences, like I did on a certain September evening we don't discuss. I'm out. Keep the fluid fresh and the shift smooth.